Okay, good morning. All right, so today we're going to start talking about gases and the gas laws. So we'll look at the first couple of topics from chapter 10, which is gases. So we did 5, which is thermochemistry. Now we're going to jump up to 10 and deal with gases. We'll try to connect it to energy a little bit. The relationship between the behavior of gases and energy are connected. So we'll talk a little bit about that more toward the end of the chapter. But we'll start with some conversions of pressure. Okay, and then we'll get into some of the basic gas laws. Tomorrow we'll look at the ideal gas law, and then connect it to chemical reactions. And then after that, we've got a couple little details like partial pressures. We'll deal with that. And then we'll get into energy and the relationship between energy and the behavior of gases. Okay, so it's chapter 10. So the problems here are kind of calculation based, a lot of calculations here. Only really a little bit of chemistry in this chapter. When we get to chemical reactions and gas laws, we'll deal with that, but it's mainly elementary physics that we're going to be dealing with in here. Okay, so let's talk a little bit about gases. Gases, we all have experience with them, right? You have a little balloon, and the balloon has gases in it. So the balloon could have air. So that's a mixture of gases, right? That's a mixture. It's a solution, actually. It's a homogeneous mixture. So air is around 78% oxygen, O2, and about, I'm sorry, N2. Got a little ahead of myself there. That'd be a really cool atmosphere. And about 21% oxygen. Okay, so that adds up to about 99%. So then, you know, the rest of it is 1% is things like carbon dioxide, water vapor, helium, neon, argon, xenon, gases like that. All those add up to like a little under 1%. Okay, so sometimes people will just sort of round it and say it's 80% nitrogen, 20% oxygen, and there's your atmosphere. It does vary over time. So if you talk to geologists, they'll tell you a little bit about the history of the Earth and how the amount of oxygen has changed over time. Used to be a pretty low percentage, actually. Oxygen is, because it's so reactive, it's such a powerful oxidizing agent. There has to be a source of producing it in order for it to exist in the atmosphere. And that, of course, is photosynthesis. Photosynthesis is the source of oxygen in our atmosphere. If you look at other planets like Mars or Venus, which are rocky planets that have atmospheres, neither one of them have very much oxygen in them, right? Because the oxygen's so reactive, it's going to react with the minerals on the surface. And but the oxygen in the Earth is, you know, pretty high because of photosynthesis. That wasn't always the case. Before photosynthesis, it was much lower. So this actually gives you a possibility of detecting life on other planets, because oxygen is so reactive. If you could find a planet or a moon that had a pretty high concentration of oxygen, more than a few percent, that might suggest that there's actually photosynthesis taking place on that planet. So in the future, there are proposals to launch space telescopes that are very advanced, like the Hubble Space Telescope, but much more advanced, that would be able to make measurements on the atmospheres of what they call exoplanets. These are planets outside of our own solar system. And they might be able to be sensitive enough to measure the light that's emitted by oxygen or absorbed by oxygen, either way. And if you could make something like that, you could tell, you know, you could study different planets and see if there's oxygen, and if there is, then there might be photosynthesis, and then that would be a planet you'd want to study more. So currently, I think, I forget what the current number is, but there's, you know, probably like a couple thousand exoplanets that have been discovered using these telescopes, the Hubble Space Telescope. There's another one going to be launched later this year called the Webb Telescope, the James Webb Telescope. And that is much more advanced than the Hubble. It's like 30 years younger. I think the Hubble went up in the late 80s or early 90s. So this one's much more advanced and very expensive, but in theory, it can detect a lot of planets that are around these other solar systems far away from ours. And I don't think it's sensitive enough to measure oxygen in the atmosphere. I don't think it's set up for that, but maybe in another 30 years or so, the technology might evolve to the point where they can do that. Okay, so that's air. Air is a mixture of gases. Of course, you could also have a helium balloon, right? And we know helium is less dense than air, so it floats, right? So if you put helium in there, the balloon's going to go up. It's going to have buoyancy. So there's helium is also a gas. And, you know, carbon dioxide's a gas. So there are compounds that are gases. You know, water vapor is a gas. And then there are elements that are gases, right? And so the noble gases are definitely gases, right? So the noble gases are helium and neon and argon and krypton and xenon, and then radon. Radon is radioactive. It's actually a pretty dangerous gas. It's a heavy gas. And it is suggested that a large number of people die each year from lung cancer due to being exposed to radon because it's radioactive. So it's unreactive, it's a noble gas. So you breathe it into your lungs and it just sort of sits there and emits these particles because it's radioactive. And so those particles are, you know, essentially colliding with molecules that are in your soft lung tissue, right? And they're pretty sensitive to radioactivity. So that could be dangerous. And most people who die of lung cancer die from smoking tobacco, but some number probably died of radon. So if you have a house and you have a basement, it's probably a good idea, you know, once in a while, maybe every 10 or 20 years, just kind of check the radon levels depending on where you live. Some areas, if you have granite, if granite is the, you know, the rock that you're built on is granite, granite tends to have radon. And so it's something you want to check. Okay. You can buy little kits on Amazon now and check the radon level. Okay, so those are some gases. What do we know about gases? Well, you know, one of the big differences between gases and other materials are that gases are very diffuse. They're not very dense, right? You can walk right through air very easily. You don't even really notice it's there unless you're running. Then you can kind of feel it a little bit, right? Or if you're in a car, you can feel it if you're going fast. What you're feeling is those molecules just kind of slapping against your skin, and they exert a force on your skin if you're going through. And there is a force on us all the time due to air pressure, but we're so used to it, we don't even really notice it. But air molecules or gas molecules are generally very diffuse. They're not very dense. And so, you know, they're pretty widely spaced. And then if you take a look at the same material, condense it down into a liquid. Condensation is when something condenses. You condense it down into a liquid. The liquids actually would just occupy this little tiny space here, right? So that's why you can get those water droplets. You often see them on cars, right? In the wintertime or in the fall or the spring usually, right? Actually less in the wintertime, more like in the fall. So there's humidity in the air, there's water in the air, and then it cools off at night. And, you know, metals and glass are, you know, will allow that surface, the surface will cool off, and then the water droplet, the water molecules will condense into a liquid. And you get a thin layer of water, right? And so if you compare the liquid, you know, the space that a liquid takes up compared to a gas, it's much smaller, right? This is like 1,000 times smaller space than the gas is there. And then of course, the same is true with solids. Solids are pretty dense as well, right? So a solid might even be a little more dense with the exception of water. Water is an unusual material. The liquid's more dense than the solid. But, you know, your solid, what's the difference between a solid and a liquid? The solids generally, the particles are really kind of stuck together in an orderly way. and they can't really move with respect to each other. Whereas in liquids, the molecules or the atoms are able to kind of move around, right? They have translational motion, so they can flow, right? So liquids flow. If this was an ice cube in here, you know, then that ice cube wouldn't be able to move, right? Because the atoms, the molecules are locked in together. So it's important to point out that the density of a liquid is approximately the density of a solid. They're about the same, but they are much greater than the density of a gas. A gas is usually about 1/1000th the density of a liquid or a solid. And again, ice is a little less dense than liquid water, and that's why ice cubes float. They're a little less dense, okay? So those are some differences. Now, it turns out that in terms of the physics of this, when you have molecules that are really far apart from each other, they're kind of acting independent of each other, right? Like they don't really even, know each other's there. Whereas if you're talking about liquids or solids, they're all interacting with each other. And, we'll try to talk a little bit about those interactions. What are they doing with each other, the liquid molecules to the solid molecules? We'll talk a little bit about that later in the course. But the gas molecules are not really interacting with each other. They do collide. They're moving, right? They're not stationary. So they move in directions random, pretty random, right? And so they collide with each other, and they collide with the walls of the container too. And when we get into the kinetic theory of gases at the end of the chapter, we'll talk more about that, okay? They're moving around. So it turns out when they're behaving that way, it's mathematically, it's easier to kind of develop a model, a mathematical explanation for what's happening to make predictions. That's a lot easier for that. This is harder over here because of those interactions. Those interactions complicate it mathematically. So what happens is we have these what we call gas laws. And when we say gas laws, we mean just like little mathematical relationships like PV equals nRT or PV equals a constant, stuff like that. Those are gas laws. You don't tend to have those. There are no real liquid laws or solid laws because those materials are so complex in terms of their interactions. There is no simple equation that you can use. This is pretty simple. This is pretty simple. There aren't simple equations for liquids or solids. So for that reason, we have an entire chapter dedicated to gases. If we had simple laws that we could devise for liquids or solids, we would probably have another chapter that's about, the liquid laws and the solid laws, but we don't have those. There is a chapter in your textbook about liquids and solids, but they're all kind of lumped in together. And it's really a pretty descriptive thing, just like, oh, these behave this way, these behave this way. But not coherent in the sense of the gases, that here's the equations we're going to use to describe the gases, and we're going to do those calculations, okay? All right, so the first thing we're going to look at is we're going to look at pressure. And we talked a little bit about a pressure with PV work, right? Okay, so let's remind ourselves about pressure. Pressure, P, can be defined as the applied force divided by the surface area, divided by the area, or just force over area, right? Now, I'm not going to go into the details about what a force is. If something is accelerating and it has a mass, that generally means there's a force being applied to it, okay? But you can think of it kind of in practical terms, right? So like if you take a pencil and that pencil is pushed against the surface of a piece of paper, okay, and you push down, right? So really what you're doing is you're pushing down. There's a force that you're applying, right? There's a force. And even though they have the pencil at an angle that's not normal to the surface, there is a force downward, right? So you're pushing down on the paper. And then that's really just a practical issue, that way our hands are constructed. So as you push down, you slide across. What happens? The little atoms of carbon that are in that pencil lead, those atoms are essentially pushed onto the surface where they break apart. They just essentially, the pencil lead is crumbling And it just does so in such a way that it is practical. And then you slide it across, and there's a force in this direction as well, right? You're applying a force this way as well to move it. And so that those atoms are just being spread out across the surface, and then you're writing, right? So same with a pen, essentially. Okay. With a pen, the stuff is a liquid instead of a solid. Now, that's a force we're applying, right? So we're applying a force. And if you think about it, the force depends on the area, right? I mean, not the force, but the pressure depends on the area. Because imagine this. Imagine that I had a pencil that had a pencil lead that was like this, right? So suppose that was the pencil lead. So actually, kind of at the atomic level, that's sort of what it looks like. And then I apply this force. So if I apply this force here, if I were to apply the same force over here that I apply here, okay, same force, right? What happens is this. The same force here has a larger area of, a larger area of contact, right? There's a large area. This one right here has a very small area, right? Very small area. So what happens is the forces are the same. The area is going to determine how big the pressure is going to be, right? Because if the force is the same, but the area is smaller, if you make this smaller, the ratio gets larger, right? Like if you have P equals, I'll just make up a number, 10 over 10. So suppose our area is 10. Well, then your pressure is 1. But suppose I say, oh, I'm going to have the same force, but I'm going to make the area much smaller, just make it a 1. Well, now you have a larger pressure, right? So the pressure, not only does it depend on how strong the force is, it also depends on how large the area is. And that's essentially the idea of a hypodermic needle, right? The needle is so thin that you can inject it into the skin, right? It just goes, it's not like it's actually squeezing through the atoms. It's just breaking through the skin. Now it's breaking through a pretty small piece, but it's breaking through the skin because the pressure is so great, right? It's such a thin thing. So the smaller your needle, the easier it is to puncture it in through the skin. You get a larger and larger pressure. So what are these units that we're talking about? And it turns out for pressure, there are many units, but let's talk a little bit about one possibility. So pressure equals force over area. You know, when you think about the MKS system, the meter kilogram second system, chemists used to use the CGS system, which was centimeters, grams, and seconds. But, you know, we're moving towards the MKS system. So your length is in meters. And the abbreviation for meters is M. Your mass is in kilograms. And the abbreviation for kilograms is kg. And then time is in seconds. And your abbreviation for seconds is S, right? So force is meters, kilograms. These are the units. Kilograms, meters squared, meters per second squared. So that's the area of force, the units of force. But the units of area is length squared, is meters squared. So you get this kind of weird combination of units here. So sometimes what people will do is they will just cancel the meters and you'll get kilogram per second squared. Now both of these are in the denominator, so times meters. So you might see it that way, kilogram per second squared per meter. So that would be the units that you have with the MKS system. But that's so awkward that usually what people will do is they'll give names to the units. So the units of force, kilogram meter per second squared, that's generally called a Newton, N-E-W-T-O-N. And the abbreviation for a Newton is an N, capital N. So that's what we call a derived unit. Derived meaning it's a combination of different units, mass units, length units, and time units. And then what people will do is they'll say, wait a minute, okay, pressure is force over area. we'll put in the unit Newton there, and then you put in your meters squared there. So see, we're not canceling any units here. So it's just newtons per meter squared. So that would be your pressure unit. But again, that derived unit is kind of awkward to call it. Hey, how many newtons per meter squared do you have? So usually what people will do is they'll call it a Pascal. So a Pascal is a Newton per meter squared, and the abbreviation is a PA, right? Why is it not P? I'm trying to think. There's some unit that uses a P, Poisson maybe. I'm not sure which one it is. But in any case, it's Pascal, so it's PA. So force units are in newtons. Pressure units are either newtons per meter squared or pascals. But the problem with a Pascal is it's a really small unit of pressure for everyday life. And so let's talk a little bit about that. So here's our first unit. We have the Pascal, okay, which is a Newton per meter squared. But there's a certain issue with it being very impractical. So let me go over these pressure units. Okay, so here's an older unit. It's called the torr. Okay, it's also the same thing as what's called a millimeter of mercury. It's really the same unit, just a different name. So it's either a torr or a millimeter of mercury. Okay, here's what happens if you take a pool of mercury. Okay, so this is liquid mercury. And then you take a tube. Generally, you want to have it to be transparent, so either plastic or glass. You make a really long tube, like a yard, a meter long, like that long. And you evacuate it, meaning you pull all the air out of it so that it's completely empty. You plug up the end here while you're doing that, but you essentially turn this into a vacuum. Okay. And then you just plunge it into the liquid. So now the opening is in the mercury. Okay, here's what will happen. The atmosphere has a pressure. It has a force that's being applied to the surface, all surfaces really. So it's pushing down. The air is actually pushing down on this mercury, on the surface of the mercury. And what will happen is the mercury will then flow into this tube. And it'll go up, and then it'll stop. It won't go any higher. And the meniscus at the top actually is, it's the opposite of what it would be water. For water, the liquid, you can't really see it because this is so wide, but the water kind of bows down and the minimum is at the center. For mercury, it actually bows up. It actually goes up. And so there's a maximum as opposed to a minimum, and that's in the middle. So I'll try to draw that in there, okay? So this will fill up with mercury. And here's the cool thing about this. The height of this mercury, so the height, what is the height? The height is the distance between the, where the tube begins and the maximum, okay? So how high up does it go? That height is directly proportional to this pressure. I'll call it external pressure. It's the atmosphere, right? It's atmospheric pressure, but we'll call it external. So the height of this mercury is directly proportional to this pressure, external, okay? So what that does then is it gives you a very simple way for measuring the air pressure. All you got to do is have a mercury pool, like a little, like a little cup, fill this with mercury, put a tube in it, and then measure the height, okay? And that height will be proportional to the atmospheric pressure. Now you can actually, I won't go through the derivation, you can actually turn it into an equation. And I'm sorry, the external pressure is equal to the density of the mercury times G times H. So we know what H is. This is the density of the mercury. This, unless you've taken physics, you may not remember what it is. This is called the gravitational acceleration of the Earth. Okay, gravitational acceleration of the Earth. Okay, and its value is 9.81. I can't remember the other digits. You have to look it up. 9.81 meters per second squared. 806. Okay, I think I'm starting to remember. 806 meters per second squared. It's an acceleration. So the units are meters per second squared. Okay. All right. The density of mercury is 13.6 grams per milliliter. That would be actually in CGS units because a milliliter is a centimeter cubed. But in the MKS system, it's 13,600 kilograms per meter cubed. So there's your density, right? So that, boom, that allows you to calculate the density, I'm sorry, the pressure of the air just by measuring the height. And guess what happens? It's kind of interesting. What happens is under normal conditions, so let's say it's room temperature outside and you're right at sea level and there's no storms coming, so the weather is kind of, you know, calm. You're going to get a value that's pretty much the same all the time. And that value is around 0.76 meters. Which is also equal to 76, I'm sorry, 76. Did I that right? 76 centimeters? Yeah. 76 centimeters or 760 millimeters, right? A millimeter is a tenth of a centimeter. So that's the height you would generally get under normal conditions. Now, if you're up at a high altitude, like in a mountain, it'll be less. If you're below sea level, so if you're like in Death Valley or the, what is it in the Middle East? It's the Dead Sea, right? I think the Dead Sea is below sea level, right? If you're there, you'll have a different pressure. It's not a big difference, but there's a little bit. But at sea level, it's 760 millimeters or 0.76 meters. So what that does is it allows you to calculate the external pressure, right? We have all the values, we have the density. So let's do it in the MKS system. So the pressure would be 13,000, I'll write it here, 13,600 kilograms per meter cubed, right? Mass per volume, 9.806 meters per second squared. And then your height is 0.76 meters. Okay. So what are we going to get in terms of units? It's a pressure, right? So it should come out, you know, we're using kilograms, meters, and seconds. So it should come out to our pascals. It should actually be pascals. So it should be, you know, kilogram per meter second squared. And it will, right? You're going to have kilogram. 2 of these meters cancel with 2 of those. And then so you've got kilogram per second squared per meter. And so it's nice. Okay. So 13,600 times 9.806 times 0.76, and you get 101,300. And then, you know, it's kilogram per meter second squared, right? I'll write the meter before the second squared. That's the same as a Pascal. So 101,300 Pascal. So look how big this is. That's a big number, right? So for that reason, what people will do is they'll say, look, that's just a ridiculously large number. So let's use a prefix. Let's use kilo. If you use kilo, that's 1,000. You're just going to move this to the three places. So you get 101.3 kilopascal. That's more practical. Hey, what's the pressure? 101.3 kilopascals, as opposed to 101,300 pascals. So you'll see pascals, but you'll also see kilopascals. And this is the equation that it comes from, right? And what's going to vary? Well, if you're using mercury, that's never going to change. If you're using the Earth, right, it would actually be a different value on the moon because G is different on the moon. But if you're on the Earth, that's not going to change. That's 9.806. What would change is the height, right? So if a storm is coming, the pressure will change. If a storm is leaving, the pressure will change. Your air pressure can change depending on the weather, but it doesn't change by 20%. It only changes by like, you know, 1% at most, or 2%, I guess. I'm not a meteorologist, but it only changes a little bit, okay? Go up high altitude, now it starts to change, right? But in any case, at sea level, that's what you're gonna get. So that's not the exact value because I didn't use the right number of sig figs on G, and I didn't use the right number of sig figs on Mercury, but let me give you what the values are. So we're gonna call it 1 atmosphere pressure. Right, so that's the sea level situation. I'm going to write it as an abbreviation. 1 ATM, that's an atmospheric pressure, is equal to, remember I said 76 centimeters, so you could write it this way. 0.76 millimeters of mercury. See how that's written? Millimeters of mercury, because we're using mercury in that device, which is called a barometer, by the way, barometric pressure, which is the same as 76 centimeters of mercury. It depends on the liquid. So if you're using water, you'll have a different value. And then 760 millimeters of mercury, right? So those 4 different units right there. But now there's even more, right? Because a millimeter of mercury is the same thing as a torr. So this is also equal to 760 torr. So the tricky thing about gases is you're going to see all these units. They'll tell you the pressure is 750 torr, or the pressure is 750 millimeters of mercury, or the pressure is 0.75. This is meters. I'm sorry, meters of mercury. So you're going to see all these units in these problems. So you just have to make a little table for yourself. An atmosphere is 0.76 meters of mercury, which is 76 centimeters of mercury, which is 760 millimeters of mercury, which is the same as a torr. So 1 atmosphere is also 760 torr. But then we've got this Pascal, right? So 1 atmosphere is also 1.01325 times 10 to the 5 pascals. So there I just put it in scientific notation, but it's also equal to 101.325 kilopascals. So a lot of units here. Are these all of them? This isn't even all of them. There's another one. 14.7 PSI, pounds per square inch. Okay, so PSI. I don't think there are any problems in the ALEKS where you do PSI that I've assigned, but you'll see it in textbooks all the time. So in any case, there's a lot of units here. So this is all 1 atmosphere. There's another unit called a bar. So 1 bar, BAR, it's kind of like a kilopascal. So I'm going to write it this way. It's 100 kilopascal. So all we've done is I've rounded 101.325, because what happened was you're so close to 100 there that the physicists were like, what the hell, what are we doing? Like, why are we using this? So let's do this. We can't change what an atmosphere is because that's already been known and it's defined. So getting people to change agreements on that's crazy. So what they decided to do was, let's just invent a new unit that's almost an atmosphere, and we'll call it a bar. So a bar is like almost as much as an atmosphere, right? It's 100 kilopascal instead of 101.325. So you'll see this out there too. If you do geology, they use bars. If you do pressure, they do bars. I mean, if you do physics, they do bars. Like high pressure physics, they do bars. And then you can always have prefixes, right? Like kilobar, gigabar, kilo atmospheres, giga atmospheres. So you can throw that in there too. So there's a lot of possibilities. Okay. So a lot of background there, a lot of background on that, but these are the units. So let's take a look at a problem. Okay. I'm going to open up the first one. Okay. Interconverting atmospheres in kilopascals. So here we go. This is atmospheres in kilopascals, right? So the partial pressure of carbon dioxide in the atmosphere is 0.000314 atmosphere, pretty small, right? Calculate the partial pressure in kilopascals, all right? Rounded to 3 sig figs. That measurement, by the way, has 3 sig figs, right? 314. Remember, leading zeros are not significant. Trailing zeros are. This one doesn't have any trailing zeros. What do they call them? Captive zeros are significant, but this one doesn't have any either. So it's just 3 sig figs, okay? So why they didn't put that in scientific notation, I guess just to have you figure out how many sig figs were in it, okay? So we're gonna convert that to kilopascals. So 0.000314 atmosphere. And we want to go to kilopascals. So the conversion for that's pretty straightforward. 1 ATM is 101.325 kPa. Okay. There's your kilopascals. Okay, so we want to go to kPa. So we're going to put the kPa in the top. So 0.000314 ATM. And then 101.325 kPa divided by 1 ATM, right? I'm just using this conversion factor here. Atmospheres cancel. And so it's going to be still pretty small. It's going to be less than a kilopascal, I guess. So 0.000314 times 101.325. And I get, it's still pretty small, 0.0318, 3 sig figs, right? kPa. Okay, so this is an example where maybe you'd want to use pascals, right? Because if you move it over 1, 2, 3, you get 31.8 pascals, right? But people often want to use kilopascals, not pascals. So that's why they asked you to do that. Okay. Okay, that's the first type of problem. The second type of problem is converting atmospheres and torrs. So let's look at that one. Interconverting atmosphere and torr. Right? Torr is the same thing as a millimeter of mercury. 760 torr is 1 atmosphere. So the vapor pressure of ethanol at 25 degrees Celsius is 58.7 torr. Calculate the vapor pressure in millimeters of mercury and atmosphere, rounded to 3 sig figs. So 58.7 torr. So 58.7 torr. And we want to go to millimeters of mercury and to atmosphere. Okay, so 2 conversions, but torr and millimeter of mercury are the same thing, right? Because as I said, 1 atmosphere is 760 torr, but I also said 1 atmosphere is 760 millimeters of mercury. They're the same. So no problem then. That means it's just 58.7 millimeters of mercury. Right? You could go through the conversion, but there's no need to. They're the same thing. It's just a different name for it, right? So like if I said, you know, 58.7 kilogram per meter second squared, And then the question was, how many pascals is that? It would be 58.7 because a kilogram per meter second squared is the same thing as a Pascal. Okay, so that's easy. Let's do the atmosphere though. So we have 58.7 torr. And 1 atmosphere is 760 torr. The torr is actually pretty practical. The torr is pretty practical, you know, we use it quite a bit. So 58.7 divided by 760, and you get a pretty small number, right? Now, here's what's nice about the atmosphere. We know what an atmosphere is. We walk around in it. So like if you think about it, this is like 7.72%, right, of an ATM. Right, 0.0772 is 7.72%. So like it's like you have like kind of a practical way of thinking about it based on your experiences. Oh yeah, it's like, you know, less than 10% of the atmospheric pressure. So you would know that you'd have a problem breathing in that, right? Like if I took away 92.28% of the air, you'd have a tough time breathing, right? So that's kind of useful to have it in atmospheres. Okay. All right, so that's that one. So now let's head into, oops, sorry. Let's head into the next topic, which is the gas laws. Okay, so let me come up here. And we're going to talk about the gas laws. So this is 10.2. Okay, and there's a bunch of them. So we're going to start with Boyle's law. Okay, and then we'll go into Charles's law. And then we'll go into Avogadro's law. Okay, I think those are the 3 laws that they have you. Sometimes Charles's law is also considered, oh shoot, I forgot his name, I'm sorry. Oh, I can't remember his name. We'll just call it Charles's law for now, until I remember his name. Okay, so let's start with Boyle's law. So Boyle's law is based on the gas cylinder, right? Remember our gas cylinder from chapter 5? So you take like a cylinder and you put a piston in it, right? There we go. Then you put a gas in here. And then you apply a force, right? This is the piston. And the whole thing is called a gas cylinder. So that was important when we were doing mechanical work, right? Compressing a gas, doing work on the gas, expanding the gas, doing work on the surroundings, right? Or the gas is doing work on the surroundings. So same idea here. Now what we want to do is we want to look at the relationship between pressure and volume. And, you know, we've already kind of done this, right? PV, right? Pressure, P is pressure and then V is volume, okay? So what's the relationship? The relationship is that if you compress a gas, so if you do compression, we're not talking about energy right now, we're just talking about the volume. Here's what happens. If we compress the gas into a smaller volume, there we go. So there's your gas now. Well, how do you compress a gas? You have to push down on it, right? So you have to increase the pressure. And what we said in the last chapter was that the pressures, when you stop compressing it, when it's no longer moving, when you're no longer moving the piston, the 2 pressures are equal, meaning the external pressure, that's the pressure you're applying with the piston, is equal to the pressure of the gas, right? The 2 are pushing each other. They're going to have equal pressures. Okay. So that means the following. If it took more pressure to get it compressed, the pressure on the inside is going to be greater than it was at the beginning. So that leads us to a following relationship. Compressing a gas increases its pressure. And a way of putting this mathematically is that as V decreases, P of the gas increases. Okay? They're inversely proportional to each other. As one goes up, the other one goes down. So this is going to have a higher pressure here than it had over here. And the same is true for expansion. So for expansion, okay, so we'll start off here. So here's your gas. Expansion so now the gas has more volume, right? Okay. So as the volume goes up, the pressure goes down. Okay, so if you allow a gas to expand, at the end, its pressure will be lower than it was initially. Okay, so that's our relationship. So we can write this mathematically. There's different ways to do it. One way would be like this. Volume is proportional to 1 over P, right? As pressure goes up, volume will go down. Or you could write it as P is proportional to 1 over V. You could write it that way too. Another way to do it is PV is proportional to a constant. So the pressure times the volume is constant, okay? So sometimes you'll see it that way. PV equals a constant. I'll put K for constant, okay? I guess you could call it Boyle's constant. But here's the practical use of it. The practical use is to say, hey, we have an initial pressure and an initial volume. So P1, V1. And then we have a final pressure and a final volume. And so what happens is P times V is constant. So that means whatever P is, if you multiply it by V, no matter what the conditions, you're going to get the same answer. So if I double the pressure, I cut the volume in half, and it's still going to be the same product. So the way to write this then is P1V1 equals P2V2. And that's a practical form of Boyle's law. All these other equations are true, right? V is proportional to 1 over P. P is proportional to 1 over V. P times V is equal to a constant. But this is a sort of the practical use of it. P1V1 equals P2V2. Okay, so let's take a look at an example. Okay. A cylinder is filled with 10.0 liters of gas. Doesn't say what the gas is, doesn't matter. That's the nice thing about these. And a piston is put into it. The initial pressure of the gas is measured to be 225 decimal kilopascals. The piston is now pushed down, right? So as you push it down, the pressure is going to go up because the volume is going down, right? Compressing, volume gets smaller, so pressure's got to go up. Compressing the gas until the gas has a final volume of 4.40 liters. Calculate the final pressure of the gas and then round it to 4 sig figs. Okay, so P1V1 equals P2V2. You know, I would say make V1 10.0 liters, make P1 225 decimal kilopascal. So there's your P1V1. And then that's going to be equal to P2V2, where V2 is 4.40 liters. And then you calculate P2, okay? So let's take a look. Okay. Got your 10.0 liters and the initial pressure. They tell you initial pressure. So P1 is 225 kilopascals. And that's the pressure at 10 liters. So that means that's V1. And then they tell you you get a compression. So now your volume is equal to 4.40 liters. So let's call that V2, right? And then the question is, what is the pressure at that volume? That's what P2 is. What is P2, okay? By the way, you can write it this way. P1 V1 equals P2 V2. Notice the similarity between that and the molarity equation. You know, when we were doing molarity, M1 V1 equals M2 V2, similar form, right? But sometimes people will write it this way, PI VI, initial pressure, initial volume, equals PF VF, right? Final pressure, right? Final volume. So here I equals initial, F equals final, but here, you know, 1 equals initial, and then 2 equals final. So it doesn't matter. Either one, it's the same equation. It's just what you're using for the symbols, okay? So P1 V1 equals P2 V2. We want to know P2. So divide both sides by V2, right? Okay, so we need the initial pressure, which is 225 kilopascals, times the initial volume, which is 10 liters. And then we're going to divide that by V2, which is 4.4. What it's going to go up, right? If you divide by a smaller number, you're going to get an increase. Meaning if this one is smaller than this one, then the final pressure is going to be larger than this one right here. So that's 2250 divided by 4.4. 2250 divided by looks like 511. Okay, right. Kilopascal is there. Liters cancel with liters, right? You don't cancel the kilopascal, sorry. Kilopascal. So those are your units, 511 kilopascal, right? So it's kind of consistent with what we said, right? If the volume goes down, the pressure is going to go up. If the volume goes up, the pressure is going to go down. In this case, the volume went down from 10 to 4.4, so the pressure went up to 511. So a little more than twice as much, right? Yeah. Okay. So there's your Boyle's law. So, you know, Robert Boyle was the one that figured this out. He built something in his house and was able to make these measurements to compress these gases to lower levels and measure the pressure. And kind of cool stuff. Did that a long time ago. So the next one is solving applications of Boyle's law. Okay. Okay, so let me, let's bring this one up. A marine biologist is preparing a deep sea submersible for a dive. The substore is breathing air under high pressure in a spherical air tank that measures 66.0 centimeters wide. Spherical, that's the key to this one. The biologist estimates that she will need 5,900 liters of air for the dive. Calculate the pressure to which this volume of air must be compressed in order to fit into the air tank. Write your answer in atmospheres and then round your answer to 3 significant digits, okay? So, you know, the idea here is you have a tank, you compress air into it, right? More than an atmosphere, right? You make it more than an atmosphere, and that allows you to use the air, okay? So they give you the size of the tank. The size of the tank is the width. They give you how wide it is. It's a sphere, right? A sphere has a diameter, so they're giving you the diameter. So from that diameter, 66.0 centimeters, you can figure out what the volume is according to the equation for a sphere. Then they say, okay, well, this is how much air you need. This is the volume of air that you need. Calculate the pressure of that volume, okay? There you go. So let's draw a little picture so I can show you what's happening. Okay. So you got this little sphere. And they tell you how wide it is. So the diameter is 66.0 centimeters, okay? So from that, you can get a volume. Now, what's the equation for, how do you figure out the volume? Oops, I'm sorry, it looks like, oh, there we go. What's the equation for the volume of a sphere? V for volume. It's 4/3 pi r cubed. 4/3 pi r squared. Remember, the area of a circle is pi r squared. The volume is 4/3 pi r cubed. So you could write that as 4/3 pi d over 2 squared. I'm sorry, cubed, right? The diameter divided by 2, right? The radius is half the diameter. So there's your radius, and there's your diameter, right? So the radius is half the diameter, okay? We have to decide what units we want this in, okay? So they're playing around with a little bit of the units there. So it's 66 centimeters. I'll show you what to do with the units in a moment, okay? Now, when you fill this up, okay, when you fill it up, the pressure is unknown. We don't know what pressure we have to fill that up. You don't want to fill it up at 1 atmosphere, because once you take it down there, that's not going to be the air that you need. You need to store it at high pressure. Pack it in with the air and then take it down, and then you've got lots of air to use throughout the whole mission, right? So what I'm going to do is I'm going to call this V1 and P1, okay? Now, once you do the submersion, right, once you do the dive, you're still going to have this tank, but you're going to let the air out. And you're going to let the air out slowly over time, and it's going to expand, and you're going to get 4,400 liters. So that's your V2. Okay, 4,400. I mean, do I have that number right? 44. I'm sorry, it wasn't 4. I don't know where I got 4,400. It was 5,900 liters. Okay, so that's your volume. And then the pressure down there is going to be 1 atmosphere, right? When you're in, it's actually probably not going to be 1 atmosphere. I think when they do these dives, they don't put it right at 1 atmosphere. I could be wrong, but we'll assume that it's at 1 atmosphere, okay? So the volume, think of that as sort of like the volume of the whole submarine, and then the pressure is 1 atm, if you want to think about it that way, okay? And then what we're saying is, what pressure do we have to put it under to get all of that 5,900 liters into that small tank, okay? So P1V1 equals P2V2, and we're really just trying to find this P1. So divide both sides by V1. Okay, and then you're set. Now, P2 is easy, it's 1 atmosphere. And did they say what units they wanted in? Okay, I don't see. Actually, in the answer they might. In the answer they might tell you what the units they want them to be in. Looks like it's atmospheres. Okay, that's good. So we'll just put it in atmospheres. Okay, so 1 atmosphere now. What's our volume 2? 5,900 liters. Now, what about V1? We got to calculate V1. So I'm going to go through it with you right now, okay? Here's the little trick I want to show you. If you take a look at it, let's talk about the diameter. The diameter is 66 liters, 66 centimeters, right? 66.0 centimeters. Here's what I'm going to suggest. See how this is in liters? Let's get the volume here in liters, right? So the liters cancel out. We want this to be in liters down here so that they cancel out, and that just gives us atmospheres, okay? The problem is if you use centimeters, you're not going to get liters out of it. So let me show you what the logic behind this is. A liter is kind of a funny unit. Chemists use it. It's a practical unit, but it's kind of a funny unit in terms of the MKS system. A liter is a decimeter cubed. Okay, not a centimeter cube, not a meter cube, not a micrometer or a nanometer, but a decimeter. And that's sort of an odd thing. Now, why use a decimeter? It's just a practical issue. It turns out a liter is like a practical volume. So making, you know, a decimeter cubed, it just sort of works out, right? A decimeter is a tenth. Deci means a tenth. So it's a tenth of a meter. So it's a length about like that, which is kind of like a practical length, right? A decimeter, a meter. Okay, so here's what I'm going to suggest we do. We've got centimeters. Let's convert it to decimeters. Okay, now how do we do that? Well, it's tricky. A centimeter is 0.01 meter, right? That's what centi means. A decimeter is a tenth of a meter, right? A centimeter is a hundredth of a meter. A decimeter is a tenth of a meter, okay? So let's try to figure out what the conversion factor here is, okay? So what I'm gonna do is I'm gonna do it, think about it the other way. If I have a centimeter, how many meters, okay, if I have a meter, let's do it this way. If I have a meter, how many centimeters is that? Well, it's 1 centimeter per 0.01 meter, right? I'm using this here. So your meters cancel. So you get 100. So in other words, we could write the same thing as 100 centimeters is equal to a meter. And that's definitely true. Now, what about a decimeter? Well, if I say a meter and 1 decimeter is 0.1 meters, then you get 10 decimeters. So in other words, 10 decimeters equals 1 meter, okay? So 100 centimeters equals a meter, and 10 decimeters equals a meter. So what that tells you is there's 10 centimeters per 1 decimeter. Right? Because if you have 100 in a meter and you have 10 in a meter, that means there's 10 of these for every one of those. So it's a 10-to-1 ratio. So there's 10 centimeters, or there's 1 decimeter for every 10 centimeter. Now you got a nice conversion there. So if I say that I have 66.0 centimeters, and there's 1 decimeter per 10 centimeters, okay? 1 decimeter per 10 centimeters, you get 6.60 decimeters. So there's your diameter, 6.6 decimeters. Now, why is that good? Because now when I put it into this formula here, it's going to come out in decimeters cubed, which is the same thing as a liter, which lets me put the number directly into there, instead of getting it in centimeters cubed and then doing a conversion into liters. Okay? So now here's our conversion. You divide by 10, that puts it into decimeters. So now the volume, okay, I'm sorry, volume 1, is going to be equal to 4/3 times pi times the diameter in decimeters, 6.60 decimeters, over 2, right? Because we got to get the radius. This is the diameter in decimeters, but we want the radius, so we divide it by 2. And then we got to cube it. 4/3 pi r cubed, okay? So let's do that. Remember, do the parentheses first. So 6.6 over 2. Oops. Yeah, 6.6, right? Because it was 66 centimeters. I'm sorry. So 6.6 divided by 2. We're going to cube it. So raise it to the 3rd power. And then we're going to multiply it by 4 times pi divided by 3. 4/3 pi. Okay. So it looks like you get 150.5. Now, that's decimeters cubed. Pi doesn't have a unit, 4/3 doesn't have a unit, 2 doesn't have a unit, but the radius has units of decimeter cubed, which is the same thing as a liter. So that means this is in liters. So that's why we did that, 150.5. Okay, and that's going to be in liters, which cancel. So now you have 5,900 times 1 divided by 150.5, and you get 39.2. So I'm going to round that to 39.2. Let me just write it up here. I'm sorry that it's here. Let me erase this. So your P1 is 39.2, and then that's just going to be atmospheres. And that's the answer, 39.2 atmospheres. Okay. So out of that whole derivation, okay, of, you know, units and volumes and all of that, here's what I would say. 1 decimeter equals 10 centimeters. That's all you really needed to do, right? I showed you the derivation for it, but you need to go through the derivation every time. The point is, if we do a decimeter cubed, we get a liter. And liter is very common in chemistry, okay? So if you have something in centimeters, divide it by 10 to get it into decimeters, then you can cube it to get your liters, right? Okay. So like if you had actually a cube, and it was a decimeter by a decimeter by a decimeter, let's see. Right. Then, you know, a decimeter by a decimeter divided by a decimeter, that's going to give you a liter. Okay. And it actually works out, right? If you think about it, decimeters like this big by this big by this big, right? This. So that's about a liter. Okay. So there you go. Okay, so now we're going to do Charles' law. Charles's law has to do with volume and temperature. Okay, so this is the second law, and let's read the problem, and then we'll go over it. An Arctic weather balloon is filled at 49.5 liter with 49.5 liters of helium gas inside a prep shed. The temperature inside the shed is 7 degrees C. The volume is then taken outside where the temperature is 0 degrees C. Calculate the new volume of the balloon, and you can assume the pressure of the balloon is always 1 atmosphere, and then round your answer to 3 sig figs. So notice you got these degrees Celsius in there, right? That comes into play with the sig figs, right? Because as you saw with the thermochemistry, sometimes when you subtract numbers, you end up with 2 sig figs and not 3. And so like if I took 35.5 degrees C, which has 3 sig figs, subtract, 29.5, that has 3 sig figs. Why don't we have 3? We only have 2 because we're losing 1 when we do the subtraction. Okay. Okay, so let's take a look. This is called Charles's law. Okay, Charles's law is based on the following idea. Gases compress when cooled. Oops. So if you cool down a gas, it gets to a smaller volume. So as T goes down, V goes down, right? Cooling means the temperature is going down, decreasing. Getting smaller, compression means the volume is getting smaller. So here they're directly proportional. Likewise, gases expand when heated. So as the temperature goes up, the volume goes up. Okay, so let's write this mathematically. I'm going to write it as V1 divided by T1 is equal to V2 divided by T2. Why? Because what happens is the ratio is constant. Remember how we said in Boyle's law, pressure times volume is constant? Now it's volume over temperature is constant because they're directly proportional, right? If I say something is directly proportional, divide both sides, right? So now you get V over T is proportional to some number, a constant, K, right? So the ratio in this case, unlike Boyle's where it's the product, okay? And notice I'm using the 1 and 2 subscript, okay? Now here's an important note. Do not use Celsius. Do not use Celsius in them. Use Kelvin. Because we have to use a temperature scale that has a 0 value, an absolute 0 value. Okay, so the Kelvin scale is what you're going to use. So remember, temperature in Kelvin is the temperature in Celsius plus 273.15. Okay, and then you can just go through it. Okay, so let's come back. This is the equation. That's our conversion. So let's come back and look at this problem. V1 T1, V1 over T1 is equal to V2 over T2. So notice, an Arctic weather balloon is filled with 49.5 liters of helium gas inside a prep shed. Okay, well, there's your V1. The temperature inside the shed is 7 degrees C. There's your T1, but you're going to convert that to Kelvin. You're going to add 273.15. The balloon is then taken outside where the temperature is 0 degrees C. Okay, there's your T2. But again, make sure that's in Kelvin. Calculate your new volume, calculate your V2, okay? That's the idea there. Pretty simple, actually, once you start looking at it. Okay, so V1 over T1 equals V2 over T2. And we just want to make sure that temperature is in, T2 is in Kelvin. Okay, so your Arctic weather balloon, your V1 is 49.5 liters. Your T1 is 7 degrees C. That's still pretty chilly, but you're going to add 273.15. So you get 280.15 Kelvin. Okay. Now let's do our V2. That's actually what they're asking us. What is V2? And then our T2 is 0 degrees C plus 273.15, which is 273.15. Okay, does that make sense? So now let's come back. We want to find V2, so we're going to try to find this. So V1 over T1 equals V2 over T2. Just multiply both sides by T2. And then your T2s are gone over here, and you just have V2. So V2, I'll write it this way. V2 is just equal to T2 times V1 over T1. So T2 is 273.15 Kelvin times V1, which was our 49.5 liters. And then we're going to divide that by T1, which was 280. Now, remember what we said, when you cool something, it's going to compress. When you cool a gas, it's going to compress, right? So it should be a little smaller than 49.5. But what you're going to find is it's not that different. So these big temperature changes that seem like big to us, I'll talk about that in a moment. So 273.15 times 49.5 divided by 280.15, and you get 48.3. Is that right? 48. Actually, it changed a little bit more than I expected it to, but yeah, it changed a little bit. So see, it wasn't a big change. It went from 49 to 48. It's a 2% change, right? You got about 2% change, approximately. Okay, pretty small difference, right? To us, that seems like a big, like the difference between an afternoon of 0 degrees C versus 7 degrees C, we would notice that, right? 7 degrees C, I'm going to put it in Fahrenheit. 7 times 1.8 plus 32 is about 45 degrees Fahrenheit. So 45 versus 32 Fahrenheit. That's a difference, right? That's something you would notice. But it's a pretty small difference in terms of the volume of this balloon. It's not going to change by much. Okay. That is an assumption here, and the assumption is that you have constant pressure. So in the problem, they actually do say that there's a constant pressure. So let's come back to it. If you look at it, it says, you may assume the pressure on the balloon stays constant at exactly 1 atm. We're going to get to that when we talk about the ideal gas law. It turns out that if you don't have a constant pressure when you do this, we're going to have to know what the pressure is and make some adjustments for that. It has to be adjusted. Likewise, with Boyle's law, the temperature was constant. So when you do Boyle's law, the temperature's got to be constant. When you do Charles's law, the pressure's got to be constant. And that's just an aspect of it. If they're not, then we have to take them into account. Okay. So P1 V1 equals P2 V2 pressure volume. V1 over T1 equals V2 over T2. That's your volume temperature relationship, which is called Charles. Okay. So now, we got one more of these kind of simple laws, which is called Avogadro's. And then tomorrow we'll get to, I guess tomorrow, we'll get into the ideal gas law tomorrow. Okay. All right. So let's do Avogadro's law. Okay. Avogadro's law says essentially that the volume of a gas is directly proportional to the amount of the gas, right? As you blow air into a balloon, it gets bigger, right? So the volume is increasing because you're putting more gas in. But let's be a little bit more quantitative. It's proportional to the mass. That's true. But more directly, it's proportional to the moles, the number of moles of the gas. Okay, that's the one we'll use. And so I'm going to write it using symbols, proportional to n. Okay, so it's proportional to the number of moles of gas. Now you can write this as an equation as like V1 over N1 equals V2 over N2. That's perfectly fine. The type of problem that Alex is going to give you is going to be based on the stoichiometry of the equation, which is actually a good idea. So let's take a look at this. Let me show you the problem. So take a look at this one. The methane gas and chlorine gas react to form hydrogen chloride and carbon tetrachloride gas. What volume of hydrogen chloride would be produced by this reaction if 7.27 centimeters cubed of methane were consumed? Answer, make sure that's units and round it to 3 significant digits. So for this one, you've got to be able to write the balanced equation, okay? So methane, we've looked at it before, that's CH4. Chlorine is a diatomic, right? It's one of the 7 diatomics, so that's Cl2. They're going to react to form hydrogen chloride. Well, what's hydrogen chloride? HCl, hydrogen chloride, HCl. And carbon tetrachloride, carbon C, chloride Cl, tetrachloride Cl4, so CCl4. And then you just balance the equation, okay? So let me, over here. So methane is CH4, chlorine is Cl2, hydrogen chloride is HCl, and then carbon tetrachloride CCl4. Is that right? Is that what it was? Was it hydrogen? I'm sorry. Yeah, carbon. Okay. So methane and chlorine. So methane and chlorine gas react to form HCl, hydrogen chloride, and carbon tetrachloride. Okay. Now, for these ones, make sure you balance the equations. So let's go ahead and go through balancing it. We've got 1 carbon on both sides, so we're good on carbon. 4 hydrogens here, so let's put a 4 there. And now, how many chlorines do we have? We have 4 chlorines here, and then we got another 4 here. So that's 8, right? You got 8 chlorines. So put a 4 over there. So now that's a 4. Okay, now you get a balanced equation. Good. All right, so now the question is, what volume of hydrogen chloride? So we want to know the volume here. So that's our question. Would you get if you have 7.27 centimeters cubed? And, you know, hey, no need to convert this to liters or meters cubed or anything. Just go ahead and just make sure you put the units in, centimeters cubed. And 3 significant digits, okay? So here's essentially Avogadro's law. The volume is proportional to the number of moles, okay? So here's what I'm gonna suggest. This is how to approach it. Just use your balanced equation. So if I were to say, look, suppose I said, hey, I'm gonna put in 1 mole of methane. How many moles of HCl would you get out? Well, if you put in 1 mole, every time 1 of these goes in, you get 4 of those, right? So you get 4 moles. That's essentially the stoichiometry, right? That's the relationship between the reactants and products. So now here's what we would say. If I put in 7.27 centimeters cubed, that's our volume. And it's proportional to the number of moles. If I put in 1 mole, but now I have 4 moles, right? We should have 4 times as much volume. So the volume now would go up 4 times as much. So let me show you how this, here's a more systematic way to do it. What you would say is, here's your coefficient. It's 7.27 centimeters cubed per 1 mole of methane, right? That's what we were told. Balanced equation, 1 mole. Okay. Now what I'm going to do is I'm going to multiply it by 4 moles of HCl per 1 mole of CH4. Okay. So now here's what you're going to get. Now you're going to have 4 times as much. So 4 times 7.27 is 29.08. And now it's HCl. Okay? HCl is what you get. All right? So the idea here then is that you can use the coefficients 1 and 4 as the number of moles of the substance that you have here. Okay? It's a 4-to-1 ratio, so you're going to have 4 times as many moles in HCl as you would have for the CH4. Okay? So if that's true, actually let me show, let's do it this way. V1 over N1 equals V2 over N2. Okay? So, you know, 7.27 centimeters cubed per 1 mole is going to equal V2 over 4 moles. Okay, so here's your HCl, and then here's your CH4. Okay, so now if you want to figure out what V2 is, so 7.27 centimeters cubed per 1 mole equals V2 over 4 moles. Okay. If you want to find out what V2 is, you multiply both sides by 4 moles, right? So multiply both sides by 4 moles. Okay. It's HCl, but whatever. 4 moles times 7.27 centimeters cubed per 1 mole. That would be, if you multiply this by 4 moles, that cancels and you get V2. So 4 times 7.27 is the same thing, right? 29.08 centimeters cubed. Now that's 4 sig figs, so we'll just round it to 3 sig figs. Okay, and there you go, 29.1, okay? And there you go, there's Avogadro's law. Let me show you one more. Okay. So here's a different one. Hydrogen chloride gas and oxygen, should really say oxygen gas, react to form water vapor and chlorine gas. So everything's a gas here. What volume of chlorine would be produced by this reaction if 6.0 milliliters of hydrogen chloride were consumed? This one, they only want 2 significant digits, right? Because it's 6.0. Okay, hydrogen chloride were consumed. Remember, consumed means you're a reactant. Okay, so let's take a look at that one. Okay, so hydrogen chloride, HCl, hydrogen chloride, and oxygen. Oxygen is O2, so these are reacting to form water vapor. So remember, it's not liquid water, so we can use these gas laws. I'll just point out that these are all gases. And chlorine gas. Okay, so again, next step is you got to balance it. So there's 1 hydrogen here, there's 2 there. So put a 2 maybe that would help. Let's see if this works. 2 hydrogens, 2 chlorines, 1 oxygen on the right, 2 on the left. So I'm doing my little trick here, right? Put a half there. A half times 2 is 1. Now, to make it, you know, maybe more easy conceptually, you could multiply everything by 2. But it's okay, you don't have to do this step. It's still balanced because I multiplied everything by 2. Now, what do? You got HCl is 6 milliliters. Here they use actually a milliliter is the same thing as a centimeter cube, by the way. Or a cc in medical terms, cubic centimeter. Okay, same thing. 6 milliliters, and they want to know how many milliliters of chlorine are going to be produced. How many produced? Okay, it didn't say consumed. It says produced for that. Okay, so let's use the same logic. What I'm going to do is I'm going to say V1, we'll use HCl. So V1 VHCl over NHCl is going to equal VCl2 over NCl2. Let's use that. Okay. So the volume of HCl is 6 milliliters. The number of moles is a 4, right? That's going to equal the volume of the Cl2 divided by 2 moles. Okay. So now multiply both sides by 2 moles. And that's going to give you your VCl2. Okay, so it looks like it's 3, right? Right. So the idea, think about it. If you have 4 moles, it's 6 milliliters. If you have 2 moles, it's going to be half as much. It's going to be 3 milliliters. So that would work. So this approach right here is probably not a bad one to use. So that's Avogadro's law. What this allows you to do is to say, look, if I measure what volume of this I put in, and I know the balanced equation, I can predict what the volume of this one is going to be, right? In fact, you might even do it in terms of the reactants. We would say 6 milliliters of this is going to react with 1/4. So 6 milliliters of this, 1/4 would be 1.5 milliliters. So 6 milliliters of this will react with 1.5 milliliters of that to form 3 milliliters of that and 3 milliliters of that. So notice the volumes change, and that's kind of a cool thing about gases. If I were to put 6 milliliters of HCl and 1/4 of that, so 1.5 milliliters of O2, they're going to react and they're going to give you 3 milliliters of each. Right? These volumes are not additive. This is 7.5. This one's only 6. Okay, kind of mass is conserved, right? But volumes are not conserved because you're taking 4 moles plus a mole, that's 5 moles, and you're converting it into 2 moles plus 2 moles, which is 4 moles. So the number of moles change. And that's kind of an interesting aspect of it too. So that's Avogadro's law. Those are the 3 sort of what we would call basic laws of the gas laws. So let me come over here. The next topic we're going to cover is the ideal gas law. So we'll do that tomorrow. We'll talk about the ideal gas law tomorrow. And then Wednesday, we'll get into reactions with gaseous reactants and products and gas mixtures. And then Thursday, we'll do the kinetic molecular theory of gases. And then that will be chapter 10. Okay, looks pretty good there. So I think that's about it for today, you guys. So practice these. And good luck with them. Reach out to me if you have any questions. And for those of you that are in person, we'll be doing it tomorrow. Oh, by the way, so if you're not in the in person, so if you're in the section A, 11A for the lab, tomorrow I'm going to actually try to record the video, and do it sort of live at 1 o'clock. So we'll do it at 1 o'clock. So 1 to 2, you can log into the regular Zoom. It'll be from the Kingsborough. We'll see how well it works. The sound quality is not so great, I don't think, but we'll try it. And feel free to join. I will upload it for sure. So take care. Have a great day.